And then just to give some focus on the products that we offer. I don't want this to be a commercial, but I really do want to share some of the features that we bring to the table that are, in many cases, new to this market segment. So the EV conversion market, the EV motorsport market has been around for a long time, but in many cases it's been done in small verticals and small shops where people don't have access to some of the controls that we offer. So I guess I'll just roll through this. The main obvious components, think of an RC car. You have your motor. This is a Cascadia dual stack. This is actually a 950 horsepower motor package right here to give you an idea of how powerful these are. This is a Cascadia inverter. Then you have another major component of the batteries. So that's your RC car. You have those three primary components. The inverter's job is to take DC voltage from a battery pack, turns it into AC voltage that can feed your motor. And so that's again, like an RC car, you have a little inverter that makes that conversion to a brushless AC motor. So what's really awesome about an EV car, or about an EV motor, is that you can have 100% torque on demand. You've heard people talk about how amazing they are, how powerful they are. That also means that in a direct drive system with no transmission, your foot from here to here is full throttle. That's also from 0 to full speed. So you don't have gears to run through. So that means your foot, wherever it is going to get that kind of torque and that kind of speed. So in a big, powerful motor conversion, what you'll have is when your foot is off throttle and you go from off throttle to on throttle, at full throttle, you can then get 100% torque on demand, which sounds like fun. And what we might be used to in IC cars, where the engine has to build up to a certain RPM to get volumetric efficiency or horsepower, that's when the power sort of comes on. This comes on right out of the gate. So what's really necessary is something to control this torque. So to feed it in, so you're not just in drift mode all the time. So with that being said, we introduced the VCUs. So we have two platforms. And these should really be thought about as if it were an ECU, to a degree. And I apologize, some of this is going to be really basic for I know some of the faces in here, so some of this will be very basic. But the idea is also to try to share some of the features and functions of our products. So giving the driver or the builder some degree of control is really critical. There's a slide presentation rolling. This is right here. Earlier EVs, when there was a conversion done, there was a throttle voltage signal that would go from the throttle right into the inverter. So like I was talking about, it's almost like a string, like a throttle cable. It would just, wherever you were in the sweep, is how much torque on demand you're going to have. So if you're halfway, you get 50% torque. If you're on the floor, you get 100% torque. Looking at some of the drag cars we have here, we have the ability now to bring in motorsport features or features that are tunable based on how the vehicle is going to be used. And we have map switching, which is really, really unique for the EV arena. Nothing special in the ICE or the internal combustion engine tuning world, which we've done for over 20 years now with ECUs, but this now brings motorsport features and features that you might not think about that you want to an EV conversion or to an EV race car. Examples are map switching. So the map switching can give you different torque curves based on the map selected, and some other different features as well. It might be the degree of slip between the drive and under the wheel. So using let's say you do a conversion and it's a fairly powerful conversion and your sons want to borrow the car for the weekend and you say there's no way I'm going to give them an 800 horsepower EV conversion vehicle. That's really dangerous. We have a keypad here that's CAN-based that there's a map switch button here. So you have 4 selectors you can go from. You can do like a creep mode, which we use in race cars around the parking lot or loading a trailer. But then you can give maybe half power. Now it's got a 250, 300 horsepower vehicle on Mach 3. All that information is displayed up on the dash as you scroll through if you're using our dash, as you scroll through your maps. This is Dave, everybody.
Hi, everybody.
Hey, Dave.
Hi, Dave.
Dave Stewart, development engineer, ADM Electronics. He does a lot of the applications. So the Tesla Drive board that we did, they did a lot of development on that. He's also worked with the integration of a lot of our other products. So back to the map switching. So you can now send your son out on map 2 and not worried about him going out and doing drifting competitions with your car. So it also, if it's raining or anything along that, you can bring the torque way down. It also means that your torque curve can be configured as well. So rather than it just being a linear 0 to 100%, you can have it ramped in this way, you can have it ramped in this way, however you really want it. And you can also have torque on demand by time. So using the Cobra Jet 1400 that you might have seen here last year, that was here, it's a 1650 horsepower quad motor, it's got 2 of those in it, that is a drag car, and it's an 8-second drag car. The problem again with all this torque is you can annihilate the tires, or if you have traction, you can literally put it on the bar so hard you can break the wheelie bar. So now we can have different maps to choose from, but we can also ramp in torque based on time. So this is a really trick feature. So when he launches, a timer goes, it says the car can handle 1,000 foot-pounds of torque right now. And as it goes, it ramps in the torque, or ramps out. Steve Huff's car, the 200-mile-an-hour dragster, that has a torque curve that looks like this. And it's all programmed in over time. So we can actually have that programmed in so it's not blowing the tires off mid-track, or even at the big end, or out of the hole. Nate was involved with a lot of the programming of this with a couple of the other engineers when Ford was doing the track testing with that. And it was new to us too, because the amount of torque that you can bring to the table with these things, that the first time they went to launch the car, just if it didn't have bars, it would have been on the rear bumper. So they had to keep on ramping the torque back in, and then looking at the data, and then getting it so we can actually get down the track. So those are a couple of the really cool features that the VCU brings to the table from the tuning side and from the configurability side. The other component is that these VCUs work with several different inverters and motor combinations, including the Tesla driver board that we have. That means that if you have a Hyper 9, or if you have a Cascadia inverter, or if you have a DTI with an MRX combo, all these different combinations out there, this can work with all of those different devices, which is kind of unique, and it still brings all those feature sets to the table. The other components that we have BMS battery management system. We have the keypad I touched on a little bit. This is sort of doesn't have to be this way, because some people have classic cars that have been converted, so they might want analog switches in, or they might have their own CAN set that they want to use. But in our case, we have this really easy to see. You have your Prindle across the top, you have your ignition, and then you have map switching and a couple other switches that you can set up for different feature sets. In addition to that, we have this little unit here, which is probably one of my favorites. It's called the PDU-8. So this is power distribution. So if you're a builder of a car, or someone's building a car for you, or doing a conversion, one of the greatest challenges is wiring. So when you rewire a car that was wired once, and rewiring it to accommodate all those other devices throughout the vehicle and getting power to that, you have this central location where the harness is coming from, and it spiders out through the whole car. Well, wouldn't it be cool if you're doing a conversion to be able to have the power in the location where the power distribution is required? So this unit would literally be these. How many can we run up to? Four. So 4 PDUs, and they're all CAN controlled. So this is basically a power distribution unit for 12 volts for headlights, taillights, pumps, fans, devices like that. So if you have pumps and fans in the back of the car, pumps and fans in the front of the car, contactor boxes in different locations, you can literally say, I have 3 areas of concern where I need power distribution. You take 3 of these, you place them throughout the vehicle. Now you have these little mini sub-harnesses throughout the vehicle. So you don't have an entire vehicle wiring harness. For motorsport, it's absolutely ideal. We're heavily involved in drift and rallycross and forms where the cars are getting thrashed. What that also means is that when it gets thrashed on a corner and it takes a corner off the car, they can replace a sub-harness versus the entire vehicle harness with drive and field repair. This is CAN controlled, so that means the only thing going from this to the VCU is 2 wires, which is really cool. The only thing power going to is 1 larger cable, and all the power distribution goes from here. There's an indicator light on it. There's all sorts of data coming back out of this to the VCU showing what kind of current. You have a short, you have an open. It's just a tremendous amount of information. So it gives, again, whether it's you doing the build or someone's doing it for you, it gives them diagnostic direction. So you can actually look at your data and see what's shorter, what's open, or what's wrong. The battery pack, I want to touch on BMS, okay? I'll talk about that a little bit, and then I want to talk about some of the safety features with the VCU. So, when you talk about an EV conversion, you have some major expense components. The battery pack is going to be one of your most expensive investments. And it's sometimes overlooked as the importance of what charging it and monitoring and taking care of the battery. So a battery management system basically manages the battery and keep it healthy for a really, really long time. The unique thing here is if you don't have a battery management system, if you don't have a VCU looking at all of this information, you can have things like you might have seen videos of thermal runaway on a battery pack where it melted down, or a vehicle that's underperforming, or you're destroying a battery in a short period of time because you really don't understand what you can demand of it. And a VCU, not only ours, but a programmable VCU and a properly installed battery management system can give you some information, and this is going to sound a little weird. It will only give you the power that it says it's safe to give. So you can't overcurrent draw the battery pack when something's properly set up. That means that if you say, hey man, I'm having a really good time, I want 100% of the power out of this, I should get 800 horsepower. Well, if the BMS is monitoring every cell in the pack, and there's all sorts of information that's coming up to the VCU, and the VCU says, wait, we're running a little warm, we're down on charge, so things really aren't safe to give you 100% of torque on demand. We can give you 70%. So you don't even know it, but this is all happening behind the scenes. So it's almost like knock control, to a degree in an internal combustion engine. You say, I want more boost, or I want, more RPM, or whatever it might be, but it limits the power, it trims it back to keep things safe. One of the things that we've done also is that when we first got into this segment, we got pulled into EV about 5 years ago with Rivian. Some of the OEMs. We're in Southern California, there's some smaller OEMs around us, and there's a ton of conversion shops around us, but they were using our displays as data loggers because it's a CAN-based logger, and they can replace roughly a $40,000 data logging system with a $3,000 dash cam that has some other devices that go along with it. Being that it's CAN-based was the big appeal. So we started looking at some of the conversion shops around us, and we saw really quickly that a lot of the conversion shops were doing a really beautiful job on the conversion, but the devices, the inverter or the battery management system, the contactor box, they weren't really able to communicate really well with each other. There was some analog communication, there might have been some CAN communication, but there was no supervisor system like a VCU. One of our engineers coined this as sort of the adult in the room. So it's looking at everything and communicating with everything, keeping everything in check. At that point, we're looking at what these conversion shops are doing, saying, there might be an opportunity here for us to bring a control system, in ECU. It's almost like I've used this analogy before. I was an early guy in the 80s doing tuning, and we're using all these little devices like sub-injector systems and knock control boxes and separate boost controller, all these different devices, and then trying to make them work all together, hence the term tuning, so the vehicle performed and stayed together. The conversion shops 5 years ago, when we were looking at that 4 years ago, looking at them, they were doing stuff very, very similar, making things work together, but there was no supervisor system, looking at everything, making sure that everything's playing safe and happy together, and that's where the VCU came in. So that's really the main role of the VCU. When I say it's sort of like an ECU, but it's more, because it's looking at so much information and properly set up, it brings a lot of safety to it and a lot of control to it. Circling back to the battery pack being a massive investment, or the largest part of the investment for the EV conversion, the BMS, I want to bring Nate in and sort of talk about like, what is a BMS? I've used the term, it's sort of like, think of filling an ice tray, and it's making sure that all the cells are getting filled up, equally, and not one's higher, one's lower than there, so it's trying to keep everything equal. But there's a lot more to that. So Nate, just come up, and let's talk about BMS a little bit, and then let's talk about some of the OEM-ish safety features that are woven into the VCU that keep people safe.
Okay, sure. So BMS, I assume if you're all here, you're probably sort of interested and maybe a little familiar with EV stuff. So you've probably heard of battery management system before. Who's heard of a BMS? Okay, right. So name out something you think you know that a BMS does. What does BMS do?
Balancing.
Balance cells, right? So that's one of the first things everyone thinks of, like we're gonna balance cells. So what does balancing cells mean? So just like Kirk's example, you've got your ice cube tray, right? And what we're doing is, there can be, in some cases, multiple thousands of battery cells inside your battery pack, like an Tesla Model S. There's over 7,000, a little bit larger than AA size batteries inside the car, and 16 different modules distributed throughout the car. And so all those batteries, I like to think of lithium ion battery cells as like your grandma. Like you want to treat your grandma really nice. Like you want to keep her happy and keep her warm and comfy and make sure she's in a tip-top shape and a good mood, because everyone needs to treat their grandma really nice. So the same thing with lithium ion battery cells. It's just like your grandma. You want to treat them nice and make them happy. So lithium ions battery cells like to operate within a certain voltage, just like your grandma. She doesn't like to be too hot, doesn't like to be too cold. Same thing with lithium ions. Lithium ion batteries like to operate within a certain battery voltage. And it's not very big, it's a really small window. When you charge up a lithium ion battery, it goes up to a little over 4 volts, and it discharges down to about 3 volts. So your operational voltage window is like 1 volt. So you're gonna take a fully topped off battery. So think about a car battery for a moment. A car battery is 12 to 14 volts. And you know that if you're not actively using an alternator to charge it up, it's gonna go from 12 volts down to 11 volts, down to 10, 9, 8. It's gonna have a pretty wide range of actual usable voltage. When you get into lithium ions, it's a completely different type of battery, a different type of cell architecture, and the live voltage range is really actually very small. So it only goes from a little over 4 volts to maybe down to about 3 or high 2s. So you're talking about maybe 1.5 volts of actual usable range. So in something like a Tesla Model S, you've got that AA size battery, and obviously the car is not going to operate on 4 volts. So how do you turn 4 volts into 400 volts? You take all those cells and you start stacking them up in series, and the voltage starts adding up. So you've got 4 volts, and then you put another one on top of that, and now you've got 8. And after you've put 96 of them in series, now you're operating in the 360 to 400 volt range, okay? So now you've got your fully charged up battery, and the individual little AA size battery cells don't themselves have a lot of current capacity. A Tesla large drive unit from a Model S can draw over 1,000 amps, wide open, making all the torque and power it can make. The base drive unit does 1,000, the performance drive unit does 1,300 amps. So you're talking about using a AA size battery cell that's gonna power something that draws enough to weld like inch thick steel with. So we're talking about a massive amount of current. So the way you take that battery and make it be able to support 1,000 amps worth of current is you start paralleling them up. So you put a whole bunch of them together, and this battery might only be able to do 2 amps of discharge, but then as you put 76 of them in parallel, that multiplies that up to a much bigger number. And then the discharge characteristics are very short term. So you get a lot of acceleration in the Model S for a shortish period of time, maybe 10, 15, 30 seconds, and then the battery needs to be replenished. So back to keeping lithium ion cells happy. They can't be overcharged. So you're going to go up to a little over 4 volts, maybe 4.1, 4.2. You can't take lithium ion to like 4.3, 4.5. They will start getting unhappy. Same thing on the discharge. You can't overly discharge a lithium ion cell either. So going down on the low end, there is a cutoff voltage. You can't let the voltage drop below this amount, otherwise the battery will get unhappy. And unhappy batteries result in bad things like swelling. The battery packs will bulge, and then they'll burst, and then you'll get fumage, which will catch on fire, and we've all seen those videos, and that's the last thing we want, right? So it all comes back to keeping grandma happy. So we don't want to overly charge the battery, we don't want to overly discharge the battery, and we don't want the battery to get too hot, and we don't want the battery to get too cold. So not only is voltage a concern, but how much current we have going in or out of the battery also is very important. So on the discharge side, when you're pedal on the floor, trying to accelerate as fast as you can, and your Tesla large drive unit is drawing over 1,000 amps, the battery, depending on its state of charge, how much energy is in the battery at that one moment, will determine how long you can draw 1,000 amps out of it. So if you're fully charged up at 100% state of charge, you can do multiple blasts in a row and get a lot of current. But then as you start wearing it down, it's like your bank account. Like if you start running out of money, you can't keep writing big checks, right? So eventually you're going to reach the bottom, and you got to like, okay, can't write any more checks. Same thing with the battery. As it runs down, you got to start slowing things down, and instead of 1,000 amps, we're gonna do 900, and instead of 900, we're gonna do 800, and then if you get really close, you can actually take that all the way down to like, okay, now we're just crawling. So you're gonna get 100 amps just so you can crawl up the side of the road and call AAA to get a tow. So you're trying to manage the voltage of the cell. You don't want to go too low, you don't want to go too high. You're trying to manage the temperature of the cell, and you're also managing the current in and out of the cell. So obviously we know that when we're pedal to metal, 1,000 amps, we're discharging all that current out of the battery. You can flip all that around, and we're all familiar with regenerative braking, right? So not only are you accelerating and motoring, you can come off the pedal, and your electric motor now actually turns into a generator. So that braking effect is the motor being turned into a generator. So instead of generating and making torque to propel the vehicle, we're going to use the car's momentum and actually turn the motor into a generator, spin that generator, which is now generating power to put back into the battery. So an electric motor has the capability of discharging and charging at almost the same capacity. So we can discharge at 1,000 amps, and uncontrolled, you can actually charge at 1,000 amps. So that would be like wham, back and forth, just all kinds of current coming in out of the battery. So you actually have to very closely control how much charge is going back into the battery. So on our car, like we'll discharge over 1,000 amps, but then we only allow 200 amps to go back in. So we want to make sure that, same thing is as you move more energy in and out of the pack, the resistance that it's working against is going to generate heat. So as you're using the battery more and exercising it, it's just making more heat. The batteries actually do like to run warmish, but they don't like to get hot. So you can run, and I unfortunately operate metric units, so we do a lot of Celsius. So normal day outside, it's probably 25, 30 C. You can run a battery up to 40 C, they're really happy. Once you get into like 45, 50 C, it's starting to warm up, and then past 50 C, it's like, okay, now we need to start making grandma happy and turn the AC on and cool things off. So really it's all a matter of making lithium ion battery cells happy, because if they're unhappy, bad things happen. So state of charge, pack voltage, individual cell voltage, and so the concept of balancing, what you're doing with balancing is just like on the charge up, if you're on the charger and the voltages are slowly increasing and getting close to that peak 4-volt point, since you can't overcharge any cell, whichever one winds up being the highest, because they won't be the same. Now, over time, all the voltages will just kind of drift around a little bit, and some will be a little high, some will be a little low. Well, as you're charging up, if your cutoff point is 4.2 volts, the first cell that gets the 4.2, all the other 95 could be behind, but that one cell gets 4.2, you have to stop charging, because if you continue to put charge current into the cell, it will overcharge, and then it will damage the cell, and it gets unhappy, and bad things happen. So same thing on the discharge. Just like on the top end, you'll have one particular cell that's maybe too high. On the bottom end, you might have a cell that's too low. So as you're discharging the battery and it's getting lower and lower in voltage, there's going to be a cutoff point. We're going to say that's 3 volts, right? So if one cell gets to 3 volts before the other ones, you're done. Like you can't keep going, because otherwise you risk over discharging that one particular cell. So what do we do to mitigate that problem? Instead of having these cells that are all over the place, some high, some low, we try to do what's called balancing. So the idea is to make the voltage in all the battery cells as close to the same as possible. Because what's happening is if you reach a clipping point, either on discharge or charge, you're not getting the full use of the battery. So a battery is like a gas tank, right? So it's going to have a certain amount of energy you can put into it. Now imagine you've got your fuel tank pickup, instead of being at the very bottom of the fuel tank, is like up an inch, right? So that last maybe half gallon of gas can't go into the pickup to go to your fuel pump. It's the same thing when you run into a discharge problem with the batteries. If you get so low that, okay, well, I got to protect the whole entire pack. When there's one cell that's too low, I have to stop what I'm doing, and whatever little bit of energy was left, I can no longer use because of the one cell, right? So it's kind of not making full use of your available power and energy in your battery, which is why balancing is very important, because everyone talks about range anxiety, and you have an EV, you're going from charger to charger, so things like range and being able to use your full battery's capacity is very important. So that's largely, we're all familiar with BMS as balancing, right? It's the first thing everyone says, we're going to balance the cell, balance the packs, make best use of the battery. So now we know that we're talking about very closely watching voltage, current, and temperature. And then as things get kind of on the fray, that can all get communicated to the VCU, and the VCU is the interface for the tuner to say, okay, well, now that my state of charge is dropped, I'm going to start preemptively turning down how much max power I can make. You know, because I know that if I keep just banging on the wall, I'm eventually going to run the battery down to nothing, and I'm going to be stuck on the side of the road. So we do things like derating. Like, so you can run at 100%, but not all the time. As you get closer towards the end of the capacity of the pack, you have to start throttling down. As you start getting to the end of the thermal limit of the battery, as the battery starts heating up, you have to start throttling down. Same thing if it's too cold. If you live in a climate where it gets cold at night, or Minnesota where it's cold all the time, you actually run the risk. Lithium ion, just like grandma, doesn't like to be too cold, so you have to warm them up. And you get things like active thermal management, battery heaters, battery chillers. Just like instead of being in Minnesota, you could be in Arizona where it's like 110 degrees out, and you're trying to draw 1,000 amps out of your battery, and it's heating. Just imagine grandma sweating, just being all mad and just upset. You're like, no, grandma, be happy, because we're going to cool you off. There's chillers. There's actually air conditioning that gets plumbed into the battery cooling system, and you can wick away all of that additional heat that the battery is generating and keep the battery happy, like grandma. What kind of safety stuff did you have in mind for VCUs?
Before you get into that, so they expand on, so I'll just chime in. One of the things that we saw, again, with the way other products were doing it, you might have a battery management system, like we use Orion as an example. It's a great system, but it's individually programmed. And then if you have another device over here, that's individually programmed. Our approach was to have one centralized location for programming. So the battery management system, the PDUs, are literally hardware extensions of the VCU. So they're all programmed from one centralized location. So Nate's referring to the data that's coming back, and what's the VCU going to do with that? It's also the programming that's being done from that. So in a battery management system, there's two units. There's a master and a satellite, and it's called the BMS 18 because it has 18 taps and 3 thermistors inside. So it can actually look at temps, and then it can look at 18 different modules. So the master, these are all in series, so you can have up to 18. How many units do we have up to?
12 on the 300.
12. So up to 12 total units, the master actually being one. So you can have these all wired in series, and then the master does all the collection of all the devices, of all the satellites, and then pushes it up to the VCU, so the VCU has to take it in, and that's what's in the program to take place. And the same for the PDU, all the programming is done from the VCU itself. On the safety, simple things, talk about like when you're charging, proximity, the Prindle, how it's hard coded.
Sure. Okay. Yeah, so obviously, like, kind of coming into this and to kind of further what Kirk had alluded to as far as like controls and system architecture, is prior to a product like the VCU, where the VCU is like the top tier, the top of the totem, and everything kind of architecturally falls in underneath it and it's control of it. I like to think of the older builds, which were effective, but they were kind of like controlled chaos. You have these different systems that are kind of clashing. You've got a BMS that wants to do contactor control, and you've got some kind of motor control that doesn't communicate with the BMS really. All the BMS can do is if you get too low, it's going to open contactors. Like, so instead of derating, which would be a more nicer way of throttling down, instead of just like you saying you're done, you can't drive the vehicle because like your state of charge is too low. That's the kind of functionality you would get when you have kind of this splintered system where they're not working. Everyone's heard the words. There's less synergy, right? So you've got all these kind of fragmented systems that don't really harmonize well together. And then you have something like a VCU, and it brings it all together and makes it work much more easily. So if you're familiar with lithium balance BMS, if you're familiar with an Orion, they have these things where it's like, okay, state of charge is too low, open the contactors. Battery temperature is getting high, open the contactors, because that's literally the only thing those BMSs can do, because the only thing they interface with are contactors. So that would be the same thing as like, ow, I cut my finger, I need to go to the emergency room and have surgery. Like, it's a bit of a dramatic response. Like, you don't have to go to the emergency room to have surgery. If you cut your finger, you just get a Band-Aid, right? So same thing with our system. So instead of being like, okay guys, we're getting low state of charge, open the contactors, we're gonna do like, okay, well actually, why don't we just chill out a little bit and just bring the torque limit down, or do this or do that. So there's more, finessing of the system instead of just a brute force, like we've got to stop now. So that's what that brings. And then as far as safeties go, so we've actually worked with some other systems and what we decided to do, like you might be familiar with our Tesla control modules. What we did is we knew the Tesla Model S package was going to be like a hot commodity, right? It's plentiful, it's affordable, it's high power, it's a really well engineered system, but we didn't necessarily have a good way of interfacing with it. So what some companies have done as solutions is they kind of tried their best to reverse engineer the OEM CAN control of the unit, right? So it's like, well, if we can spoof the CAN, we'll take it out of the car, put it in something else, and we'll do our best to try to make it think it's still in Model S, even though it's in a 57 Chevy or whatever it may be. So we're going to use the OEM controls, and we're going to spoof these signals and hook it up to an OEM Tesla pedal, and it should be okay. And for a while, that was acceptable and adequate. But we actually have had some very interesting experience where there's that Camaro drift car that's here. It had one of those systems initially, and when we first got it, as we started exploring what EV was, one of the first things we did is like, okay, well, let's get this thing off the ground, because if something weird happened and no one's in it, like it could just drive through a wall. So they had the car on the lift, and they're like, well, let's get this thing working. Let's turn it on. So they turn it on, and it's a touchscon system that gives away because it is. And it was like, okay, well, I hit drive, but nothing happened. Like, we'll try the pedal. No, nothing. Okay, and I hit drive, and nothing happened. Like, I don't think it's working. Something's weird. So the guy gets out of the car, and all of a sudden the wheels go, woo! We're just like, whoa, what was that? So it's a good thing the car was off the ground, because it literally would have just rocketed through and driven across Los Angeles with no one in the driver's seat. So we're like, okay, we're not going to do CAN spoofing. Like, that is not the safe, right way to do this. We need to have full integrated control of these systems, which is why what we did is we took the OEM Tesla control board, took it out, threw it away, and put it in our own system. And what we've basically done is we've hijacked all the power electronics in the inverter, the transistors, all the things that take the high voltage DC in, do the magic switching to making DC, turning it into AC, and sending it out. And we took all that and we put it in our control so that we can 100%, without question of robustness or repeatability or reliability, be able to control the inverter to do exactly what we want. So weird things like weird takeoffs because some CAN signal was unhappy, this doesn't happen anymore. It's all very protected and very safe and very kind of clean. The other approach with some Tesla controls, where there's a competitor of ours where they also made a replacement board, but the type of inverter control they chose to use was kind of basic and more entry level. So inverters in themselves are actually pretty complex pieces of machinery. I like to use the analogy of like a carburetor versus fuel injection. Like AEM, our background is engine management systems, BFI, we've been doing that stuff for 2 decades. You can take a carburetor, like you can take Holley carburetor as an example, and Holley carburetor out of a box will work on an engine that's an inline 6 200 inch to a 350 V8 to a 600 cubic inch big block Chevy. That one carburetor, because all it's doing is dumping gas into the intake manifold, and as long as you've got a trucking time spark, your engine's gonna run, right? It'll start, it'll run, and it'll probably drive on just one carburetor, right? It may not start great, it may not drive well, it may not get good fuel economy, it may not do all these things, it may pop and burp and not run nice, but it will run the engine. That is the equivalent to how that control system works. It's like an open source board where it's like a kind of a build your own, solder it together type kit. It uses a very rudimentary type of control where it's like, well, I'm just gonna put a little current here and a little current there, and that's gonna make the motor spin, and that's good enough. So that's the type of control you get. You get kind of a carburetor-esque type control with this other system, where at the deepest level, the most control you could have is called field-oriented control. And what that's doing is it's actually, there's a lot of, we all know that the electric motors work with essentially opposing magnetic fields, right? So there is a magnetic field applying a repelling force against the rotor, and that's going to push the rotor away. And then when it gets to a certain point, now we're going to pull the rotor, and that whole operation is going on inside the motor over and over and over, many thousands of times a second. So the higher end inverters do that, and they monitor it at every degree of rotation in the rotor. So it's very precise, it's very controlled, and it's very equatable to like a perfectly well-tuned, just perfect running EFI system. Like spot on air-fuel ratios. It always starts regardless of what temperature it is. I get great fuel economy. Like, it's the perfect type of control you want. That is what the AEM type control will give you when you put it into a Tesla. The other thing that we were able to do with our Tesla drive unit controllers, actually, just like you find on ICE, internal combustion engines, is the factories don't run them at 100% output, right? They leave a little bit on the table because they got to have a warranty, and it's going to last 100,000 miles, so it makes 200 horsepower, but it probably could make 250, but we don't want to run it to 250 because we got to make it last. So they leave a little bit on the table, and what we're able to do is we're able to capitalize on that. So we're actually able to realize that additional power. We can put a little more current into the inverter, drive the motor a little bit harder, and make more power. So we actually are able to make a performance gain with our controls, with our Tesla large drive units over stock. When you pair the drive unit with a more performance-oriented battery, additional benefits are realized. The battery is still, like, by far the limiting factor to performance with inverter and motors. And it's all a matter of discharge, amps, and basically current capacity, like how much can your battery really push through an inverter and through a motor. I think I got a little off track, but anyway, so back to like the keypad, so things like you can't accidentally put it into gear. So we have some safeties involved where, and this is all tunable and configurable for the end user. You get into the car, you turn on like the traditional ignition switch, and if you want, you could have it, if you're more motorsports oriented, where in the motorsports world, it's like, okay, we don't want the inverter turned on, we don't want the battery enabled until you're ready to go down the track. So you might be in the car, you might be doing like, we're gonna configure the data collection system. So car is on, but all the EV drivetrain is off. So this has what we call our ignition switch. So the ignition is like, I'm ready to drive button. So you can get in the car, you can turn on the ignition, the key switch, listen to the radio, turn on the air conditioning, do whatever, and then when you're actually ready to operate the vehicle, you hit the ignition switch. When you hit the ignition switch, that's when all the process happens of closing the contactors, bringing on the coolant pumps, enabling, telling the inverter like, hey, inverter, wake up, we're gonna start driving. It's like, okay, I'm here, let's go. So then all the systems start talking to each other, and then you can go operate the vehicle. Then once you're ready to operate the vehicle, you have to put your foot on the brake and hit drive or reverse, and parking brake disengages, and then you're able to drive the vehicle. So you can't really fat finger it, so you can't like just accidentally go into drive if you don't have your foot on the brake. So if your foot is not on the brake, you can't enable any drive mode, either forward or reverse. Another safety part that we put into it recently was that from any drive mode, if you're going forward or reverse, if something happens, you can just go right into neutral at any point, just like an OEM car will be able to do. So there's that as well. And I think Kurt, you kind of touched on, there's the performance levels, so you could have your valet mode, and I won't say girlfriend mode, maybe it's boyfriend mode, you gotta turn it on for him, it goes both ways. So there's the different performance levels. If you know that, let's say, just from a feed forward, like a preemptively, you could be like, well, the track doesn't look as prepped today, so I'm gonna actually preemptively turn the torque down versus spinning the tires. Or if you're out there drifting, you're like, okay, I need all the torque I can get. So all that is configurable and selectable right through that keypad, which is really cool.
I think you're good. We're past time right now. So, okay. So I'm hoping that, like I said, I didn't want this to be an AEM commercial, but it turned out to be an AEM commercial. But it gives you an idea of what we're not the builders, we're the controls guys. So we need the builders to integrate our product into their program to make sure that the user experience ultimately is the best it can possibly be. And that's our goal. Safety, fast, sophisticated, and information. So that's what we're trying to bring to the table.
Yeah, it's really kind of like limitless. Like, we support so many different inverters and motors. Can you talk about the CCU?
No, I didn't want to get into it, but it's not even really announced. So
it's here.
So we'll touch on this.
It's announced now, man.
Yeah, so
you guys have seen this first? No one's seen this or heard of this.
this is a new product. We refer to it as a CCU. It's actually two units. It's a DC to DC, which takes your high voltage and brings it down to your 12-volt circuit. So you could almost think of it as an alternator. And then it's also an onboard charger. It's liquid cooled. It's very compact. And again, it communicates with the VCU and it has a number of safety features built into it. So it's this is just debuting at the event. And
Very, very capable, 6.6 K output. It'll do 20 to 30 amps depending on voltage output. And it's always a specialty of AEM is our whole motto, our mantra is to make great products at very friendly prices.
So that's the thing. They also have the contactors in it too.
No, so the VCU, so the contactors are separate, and they are controlled by the VCU through the PDU or through individual outlets. But that new charger coming out, if you look around, you probably have a ballpark idea of what that type of system costs. We're not official pricing, but it's going to be very competitively priced. Like it's probably going to be the most affordable combined charger on the market. So we're super excited. It's a great, very capable high output system that I think is going to be a great fit on any EV that operates in the 360 to 400 volt range. So it's a cool little thing.
It's a great headache solver. That's nice.
Absolutely.
Yeah,
So we have like an air cooled charger on our current car, which is air cooled is like, it'll literally, in a normal operation, it'll overheat itself. Like it doesn't even run cool enough to run for more than 5 minutes. And then if the trunk is closed, like you take the normal runtime and cut it in half. If the trunk's open and the sun is shining on it, like you've got 5 minutes of charging where the thing overheats and it's like, oh guys, I can't do this anymore. So having a liquid cooled charger means you can just run it all day, all night, and it's not a problem.
right, so there's plenty more to come. You're seeing what we've finished in development, what we're going to do. There's a lot more coming for a lot of the other motor iterations that are coming down the line. So hope to be part of your builds.
When is that going to be up in the market?
This will be in the market as soon as we get connectors. We'll shortage on the connectors. So we're hoping to be within 45 days-ish based on the supply chain challenge. Shocking that we're waiting for a plastic connector to connect the head versus the electronic hardware. So that's a wrap, guys. I know we went long.
So I got some questions. So what exactly is that box? What here? This
If
thing?
you have questions, please,
What is? So tell me more about this box and how it works.
This is the VCU.
VC.
Yeah, the vehicle control unit.
And how does it? What does that do? And
So this controls everything. So all the subsystems and controls that we've been talking about are all managed by this hardware.
so so this hooked to the inverter system.
Yep.
And then
this hooks to everything. This
everything.
controls the contactors, this controls the charger, this controls thermal management, this controls the inverter, this controls the AC and DC, this controls air conditioning, this controls everything. So this is what you interface with and to with. This is
So that's the main computer of the car.
Yep. Okay. So
And
this
then-
is just big box. It's capable of running 4 independent motors and inverters. And this one is capable of doing 1 or 2. So this is like your typical builds, and this is like high-end.
So 1 or 2, like front and wheel,
Correct.
the front and back motor. This is each will have their own motor.
Yeah.
And then that's also hooked to the screen, so you can see
You
what's
can see all the
going.
data. You can data log all the data. So then what's cool about this is all the graphics are 100% user configurable. So you can use our screens if you like what they look like, or if you're savvy with like Illustrator or Photoshop, you can make the screens look like whatever you want.
Okay, that's really cool.
Yeah.
Are you guys going to come up with like screens like Tesla, like a tablet where you can do all kinds of others? Have like CarPlay or whatever?
Maybe not so much on that. We're kind of
Well, mainly
geared
focus on
towards motorsport.
motorsport,
So we have
yeah.
things with the CAN keypad and the CAN dash. So
I mean, I guess if you want your entertainment, you can have an entertainment screen, and then this is screen for your dash. So
this is basically what's nice about this is like when you put this system into an existing car, like we have a Mustang that we put our Tesla drivetrain into, and the rest of the original car stays intact. So all the wiring harness in the car doesn't get butchered. The infotainment stuff stays there, and all this system needs is like an ignition switch input, brake switch, accelerator pedal, and you've got a working EV.
yeah, and that sounds really cool. So this is the inverter system, right?
That's correct.
So they basically this takes the power from the battery and run it into this thing over here. The three. Why does it have 6? Is it 6 phase?
This is a dual motor. So this is 2 stack.
Okay.
This is a motor here, and this is another motor here. So then this is taking DC in, and it's doing dual 3-phase AC power out.
Okay.
Okay, so this is about 900 horsepower.
Okay. So yeah. So each
Yeah, so-
Each motor needs its own inverter.
Correct.
Yeah.
He came to us.
So a more entry-level system would be just, single motor, your phase cables, and a much smaller. More
And the Tesla motor, the Tesla motor you have is the board. You have a special board that plugs into the inverter of the
If you stop by
Tesla.
our booth, we have a cutaway. So
Yeah.
there's a cover that comes off, and the board, OEM board comes out, and the board is ready. 7 screws, it's in and out in 10 minutes.
And then you get that, and then you get this,
You wire it all
and then
together.
that, and then you wire, and then the wiring.
It's just like, it's an ecosystem, and you just put all the parts together, and they work together.
Yeah. So all right. Well, let me open up for all the questions. You want your questions filmed?
You guys ever talk about camera, like price pack style,
Or like to make it configurable.
or just viewable?
Oh, we publish our protocol sites. We don't not publish.
For real?
Yeah.
Okay, so that's good news because it's unlike.
Well, because all of our dash stuff has always been, like, the whole reason, like, our dash is not just limited to AEM stuff, we support, we want to work with everyone. Yeah, so anything that you can find that's open protocol,
And
we
yeah.
can consider for dash to work with.
What about, your guys' protocol right now, like,
Well, like for controls.
Yeah, yeah,
like, driving it.
like if,
Yeah,
if
it's
I
Free software, free data log right now.
but I'm wanting to have, just one intercept.
Yeah,
And display that,
It's
like.
all
CEO, yeah, CEO.
Yeah, no reason not to.
I like that. That's awesome. Cool, man.
Yeah, so
Great.
it's out there, for sure.
Do you have plans on supporting fast DC charging like CCS?
Yeah.
That's coming.
Actually, no, that actually,
They're
That's coming.
Right now, I'm trying to go to like a BMW limb and like all the,
Yeah.
secondary way, but
Right, tough.
yeah, it's a pain.
Yeah, no, that's for sure. We knew, like, we looked at the,
Is it-
kind of, took a temperature of the environment, of like, what do people need and what do people want? And CCS was certainly one of those things.
Yeah.
So it's coming.
I mean, is the fast charging going to be in that thing, or is it going to be another project after
It's a
that?
separate, yeah, it actually requires its own standalone controller that we're working on making, because there's a whole lot of protocol and back and forth handshaking between the vehicle and the charging device off board. So, and then there's like direct contactors that connect the DC in to the battery. So it's a whole kind of subsystem that operates on its own that we'll integrate with, and it'll all be controlled by the DCU.
Sweet.
Yeah, so it's coming.
All right, I can't wait.
Good news about, open,
Yeah, it's all, it's, everything we have is open.
Well, you guys located here in California, or
that's awesome. That's,
you guys located here in California, down in LA, or what?
Yes, from Southern California.
Southern California. Yeah.
That's accessible. So that's what I would encourage right out of the gate. Any guy can do it. And we're doing
All right. Well, thank you guys for watching. Check these guys out. They're making some really awesome projects and stuff. I'm trying to talk to them and doing some type of sponsorship or something in the future, but I'm not a sponsor. I just want to make sure it's filmed it so I have notes and everything.
You said that, that's all I do.
Power windows, comfort control, climate control.